You know, we think we're pretty clever, don't we? We build supercomputers, we send rockets to Mars. But what if I told you that the most sophisticated technology on Earth might just be floating on the surface of a quiet pond? For millions of years, nature's been running the ultimate R&D lab, and it has absolutely perfected solutions that we are only just beginning to understand. And the most profound secrets, well, they're often hiding in plain sight.
Just take a look at these two marvels. On the left, you've got an insect that basically treats water like solid ground. And on the right, a fern that wears a permanent shimmering coat of air, which lets it breathe forever while it's submerged. Now, these aren't magic tricks. These are masters of physics. And here's what most people don't realize. They are using the exact same secret.
So how is this even possible? How can life so elegantly defy the rules we constantly struggle with? And maybe more importantly, if we can finally decode these natural blueprints, what kind of world could we build with them? Okay, let's dive into this. Your first thought is probably surface tension. And you're not wrong, but that's like saying a supercar works because of its wheels. I mean, sure, but it completely misses the genius of the engine. The real story, the hidden truth, is so much more intricate.
It isn't just about having some waxy water-repellent coating. Nope. The true secret is an invisible architecture, a whole microscopic landscape of complex structures that are designed not just to repel water, but to command it.
Let's zoom way in on the Salvinia fern. Its surface is covered in these tiny hairs that look just like little egg beaters. And this is where the genius, the paradox, really lies. Most of the structure is hydrophobic. It hates water. But the very tips of each of those little filaments are hydrophilic. They love water. It's this incredible combination that creates the perfect trap. The waxy stalks push the water away, while the sticky tips literally grab the water's surface and pin it in place. The result? A perfectly stable, locked-in layer of air.
There's actually a name for this phenomena. It's a fundamental law of physics known as the Cassie-Baxter state. And all it really means is that a liquid can be forced to rest on a cushion of air trapped by a micro-textured surface. And because of that, the surface itself never truly gets wet.
And this diagram shows it perfectly. See the water, there in red? It never actually makes full contact. It's literally floating, held up by those blue microstructures and the air that they've trapped. It's kind of like sleeping on a perfectly engineered air mattress, but on a microscopic scale. So, nature perfected this design over eons, which brings us to the obvious next question. Can we build it ourselves? And this is the moment we go from just observing to actually imitating. And believe me, this is where things get really exciting. Using incredibly high-precision lasers, a technique called direct laser lithography, researchers have actually done it. They've successfully fabricated artificial hairs, meticulously recreating the Salvinia fern's amazing egg beater architecture.
But get this, they didn't just copy it, they made it way smaller. The natural hairs are on the millimeter scale, right? But the artificial ones are on the micrometer scale. We're talking up to 25 times smaller. Now this detail changes everything. It proves the power isn't in some special, secret organic material, it's in the pure mathematical genius of the shape itself. So the team started testing different levels of complexity. And what they found basically confirmed what nature already knew. More complexity means better performance. As you can see in this chart, the structures with 8 filaments, the most complex design, trap dramatically more air. You see, nature doesn't build things by accident. Every detail has a purpose. And the result of all this reverse engineering? Their artificial surface held a stable layer of air while completely submerged for an astonishing 100 hours. That's over 4 days. We haven't just read nature's blueprint, we've successfully started to manufacture its superpowers.
Now, this whole principle of trapping air isn't just for passive defense, like breathing underwater. It's also the key to active movement. It's the key that unlocks how to walk and, even jump on water itself.
So, inspired by the master on the left, a research team from Harvard and Seoul National University built the apprentice on the right. And their goal wasn't just to walk on water, it was to do what seems impossible, to actually jump off of it.
Now, this is a massive engineering challenge. I mean, the robot is thousands of times heavier than the insect. The downward force that needs to jump should instantly shatter the water's surface tension and send it straight to the bottom. So, how in the world did they solve it?
And this is where the big revelation comes in. The secret was completely counterintuitive. It wasn't about a quick, explosive push at all. The key, as the researchers discovered, is to do the complete opposite. You maintain contact with the water for as long as possible, spreading the force out over time. It's a carefully controlled, accelerating push, not a sudden strike.
And by perfectly mimicking this technique, the results are just incredible. The robot can push down with a force up to 16 times its own body weight without breaking the surface. Think about that. It's generating the kind of propulsive force you'd need for a jump on solid ground, but it's doing it from the surface of a liquid.
So here's the crucial point. This goes so far beyond insects and robots. This underlying principle, this microscopic architecture, it's like a master key that unlocks an entire new class of smart materials that could fundamentally change our world. Because it turns out that very same Cassie-Baxter state, that perfect little cushion of air, is also the secret behind the famous lotus effect, where water droplets just bead up and roll right off a leaf, taking every speck of dirt with them. It makes the surface perpetually self-cleaning.
Once you really grasp that, the potential applications are just breathtaking. I mean, imagine skyscrapers with self-cleaning windows, solar panels that never get dusty and always operate at peak efficiency, ship hulls that naturally resist barnacles, saving enormous amounts of fuel, or even advanced medical implants that bacteria simply cannot cling to. This isn't some distant sci-fi dream. This is the next wave of technology.
It really forces us to see the world differently, doesn't it? Nature isn't just a pretty backdrop to our lives. It's a living library. It contains 3.8 billion years of research and development. Every single leaf, every insect, is a perfected piece of technology, tested and refined through the ages.
We've just decoded the genius of a humble fern in a tiny insect. It just makes you wonder, what other revolutionary blueprints are out there, hiding in a forest, a reef, or even a simple drop of water, just waiting for us to finally learn how to read them?
Thanks for watching. Support BioVellum by liking, subscribing, and sharing. Let's explore the secrets of nature together.